go ahead and get started. So this talk is kind of a practice run for me. I'm doing this at work later. But I've done a very similar talk before with Rust. You can actually see that. Let's see. This talk here, pretty much the same thing. But the way that .NET implements Intrinsics, everything uses different names, so it was worth kind of doing this again for C#. But the same things are here. So if you're interested in SIMD Intrinsics using C or Rust, this talk is pretty much the same thing. So yeah, if you want to code along, you need Visual Studio 2019, and you need the .NET Core preview, which you can download here. And then the trick is you need to enable preview SDKs in Visual Studio. Go to Tools, Options, type preview in the search bar, and then check Use Preview. So that looks like this: Tools, Options, Preview, Previews, Use Previews of the .NET Core SDK. And you got to restart Visual Studio, and that'll let you use the .NET Core 3 preview. All right, if there's any questions, just fire away in chat. Okay, so first, what is SIMD? SIMD stands for Single Instruction, Multiple Data, and it lets you run a single instruction on many values at once. So instead of adding one value to another, you can add 4 values to another 4 values, or 8 values to another 8 values, depending on which instruction set you're using and how large of a type you're working with. So some common SIMD instruction sets that you'll find on consumer CPUs are listed here. ARM has one called Neon, and they also have a newer one as well, whose name I don't remember. Intel has a whole zoo of instruction sets, starting with MMX and then SSE, SSE2, and so on. And as you go down, you basically get wider SIMD instruction sets, which means you can operate on more values at once. But you also get new instructions, which let you more easily use SIMD on a wider variety of algorithms. Especially as you get to AVX 512, they have a lot of masking operations that really unlock a whole universe of things. So the x86 CPUs are backwards compatible with this stuff. So if your CPU supports AVX2, it's also going to support all the stuff before it as well. So what can you speed up with SIMD instructions? Just some examples here. You can people often use it for physics simulations, financial calculations, graphics. It's big in game development and graphics. But you can also use it for things people don't normally think of, for kind of computational type stuff, such as parsing and text searching. There are some popular text searching and parsing libraries that can use SIMD to speed things up, especially like finding values in a large string. You can use SIMD to go through chunks of the string at a time instead of just one byte at a time or one character at a time. Even really mundane things like memcopy can be sped up with SIMD. And in fact, a few years ago, someone figured out they could use the old system.numerics library, which gave you access to some SIMD instructions, to write a faster memcopy than the built-in memcopy in .NET, which has since been fixed, but that's kind of funny. Basically, any algorithm that isn't too branchy, you could potentially use SIMD instructions to speed it up. And just having a few branches doesn't mean you can't use SIMD. There's ways to deal with branches with SIMD instructions, which we'll talk about when we do the live coding. So which of these instruction sets should you target? The thing to keep in mind is if you use Intrinsics, you're going to be stuck on whatever hardware you're targeting, right? So if you write some code using AVX2 Intrinsics, it's not going to run on an old CPU that doesn't have those, and it's not going to run on an ARM CPU, right? It's only going to run on x86 CPUs that have AVX built in. It'll just crash or not work on something else, which is something you won't be used to with C#, because you're used to C#. You can compile it once, run it anywhere. So you will lose some of that. So your options are, if you're doing something like writing code for a server, then you just see what instruction set your server has and use the fastest one available. That's easy. But if it's something you're going to distribute to other people, then you either need to write different versions of your function using each instruction set that you want to support, or just pick the lowest common denominator and ship that. So a good choice if you're not sure what to do is just use SSE2. Anything that is a 64-bit x86 CPU is going to support it. I have some old notes here. Let's fix this. This is from the Rust talk. So if you're using .NET targeting 64-bit x86 machines, it's already going to emit some SSE2 code anyway. So you're not going to do any harm by using SSE2 in that case. Some other things to consider is once you get up to AVX or AVX2 and higher, certain instructions will cause the core that those instructions are running on to throttle and go slower. Or if you use some of the heavier weight instructions, it will cause the entire chip to throttle down. And that's just because you're doing more math, which generates more heat. The way Intel deals with that is they just switch to a different mode when you start using AVX or AVX2. The way AMD handles it is they just monitor the heat and throttle down continuously. So either way, you have to start thinking about, are you using enough AVX and AVX2 instructions, like big chunks of them, to be worth it? If you're only using a few and then using regular code again, the clock rate slowdown might negatively affect net performance. So if you're just going to pick one instruction set, use SSE2. It's kind of a no-brainer. You'll get things going faster and it'll work everywhere. All right. So how can we leverage these SIMD instructions? There's a few options. The dream, what we would all like for to be the case, is to just let the compiler figure it out. So in languages like C or Rust, anything that's compiled by LLVM, there's some auto-vectorization that can take place. So if you write a function like this, where you're just summing an array of integers, it's very straightforward. Compilers that do auto-vectorization will almost certainly figure out that they can use SIMD instructions here, and they'll generate machine code to do that. But it gets tricky if you use floating point numbers. Compilers can't switch to SIMD by default because that would change the answer. This would actually be more accurate using SIMD because of the way that floating point math works, but it would be different, and a compiler can't do optimizations that change how your programs work. There are ways in some compilers to say that this is okay, so you can like set flags to say go ahead and do this crazy stuff with floating point numbers, but it gets tricky because you might not want to do that for your whole program. You might only want to do it for one function. Some languages let you specify that that's okay for one function, some don't. Then you can get to more complicated cases where maybe you have a branch along with some math. It's very unlikely any compiler, once you start having branches in the middle, will figure out how to auto-vectorize this. But you can do this by hand. There are ways to deal with this by hand. With C#, this is pretty simple. You don't get any of this. The .NET JIT does not do any auto-vectorization, so that's just not going to happen. So that's not really an option in .NET world. Unless you're doing ahead of time compilation of C# through LLVM or something, then you could get some auto-vectorization happening. Another approach is like carefully massaging your code to help the compiler auto-vectorize it. So this would be an example in Rust of how to write this function with branches in a different way that can be auto-vectorized trivially. But again, in C#, you're not going to get this. At least not now, maybe one day in the future. Another option is to use assembler. So some languages let you do inline assembler, or you could link to an assembly library you've built and do it that way. This gives you the most power and flexibility, right? You get to do your machine instructions and manage your registers by hand, but this is very hard. And another approach is to use libraries or tools that can do SIMD for you. There is an old C# library called system.numerics, which actually gives a very nice way of using SIMD. You can write code once and the JIT will automatically generate the optimum instruction set. So back here, right, these instruction sets you looked at, you can write just one bit of code that's sort of generalized, and the JIT will figure out at runtime, okay, this machine's got AVX2, let's generate that, or it's got only has SSE2, we'll generate that. So that's really cool. Unfortunately, it's very limited. Not all the instructions are available. There's lots of tricks you can do with raw intrinsics that you can't do with this. So it's very nice to use, but not actually useful very often. There's some very simple things you can do with it. So sometimes libraries can get what you need, but a lot of times they can't. So the next option is to use intrinsics. And this is an example of what intrinsics look like in C#. Okay, we're loading data from a pointer to an array into a variable. We're doing an addition, and this will add like 4 of these values or 8 of these values at a time. Make this a float, so 4 of these values at a time, and then stores the result back in the array. So what are intrinsics? It's a weird word. They are basically special instructions. They look like function calls, like whether you're doing these in C or C#, it looks like a function call, but it's not actually a function. It's a special indicator to the compiler. And the basic idea is every intrinsic should map to an assembly instruction, to a machine instruction. So when you use an intrinsic, you're guaranteed to get that machine instruction emitted. But you don't have to manage what things go into which registers by hand like you would do if you're writing assembler. So the motivation for intrinsics is that inline assembler is hard for compilers to deal with. In fact, Visual Studio's C compiler no longer supports inline assembler at all for this reason. And the reason is the compiler is working really hard to decide, what data should I put in which registers? How do I manage registers really carefully to make performance good? If you then put inline assembler in the middle of that, putting things in your own registers the way you want to, the compiler now has to reason around your use of the registers, and it really screws things up. It makes the compiler more complicated, and your inline assembler can sometimes hurt overall performance because it's affecting the things around it. And motivation 2 is that managing registers by hand is hard, right? You have to do a lot of work to do that, and maybe you'd rather not. So intrinsics is kind of a half step between normal code and assembler. So you're dictating what machine instructions you want to use, but not having to manage the registers. Let's see. Yeah, it's good to keep in mind you sometimes can beat the use of intrinsics by large margins with inline assembler. This blog by Dan Liu, who has a really cool blog in general, by the way, shows one example of that, where the compiler just doesn't do a good job of managing registers, and he was able to find out a better way by hand. And anytime you're working with the intrinsics on the Intel side, this website's really good to keep handy. I've got it somewhere. This is the Intel Intrinsics guide. And over here you can filter by what instruction set you're using. So say you're using SSE and SSE2, and you want to know how do I add numbers? And this shows you all the instructions that match your search. You can click on one and get details about what it does. These names look really crazy. It's good to understand this naming convention because even though C# doesn't use it, C and Rust do. And if you look up, how do I do something with SIMD on the internet, you're most likely to get a C tutorial, and you're going to see this stuff, and you'll need to know how to translate it into C#'s naming convention. Basically, just stands for multimedia. The original incarnation of these was meant for multimedia. That was the buzzword back then, like when CD-ROMs were big. Then the middle part tells you what function it's doing. So in this case, adding. That's really simple. And then the end is the type. So this is for single precision floating point, double precision floating point, 32-bit ints, and so on. There's actually a useful naming convention. It looks crazy, but once you get used to it, you can read it and know what it does just from the name, right? And then in here it'll tell you, it'll kind of give you like a pseudocode equivalent of what's going to happen. It tells you the machine instruction it's going to use and so on. And if you look at the C# documentation for the intrinsics namespace, and say we click into SSE here and look at add, you'll see that they also provide the regular name. So if you're not sure what maps to what, you can look it up through here to be sure. All right, that's the standard intrinsic name, and this is the C# version. All right. Any questions so far before we start coding? Showing some examples. I'm switching over to Visual Studio. I'm going to start we're going to start out doing things the wrong way. This is the way that people commonly start trying to use SIMD intrinsics. It's exactly what I did the first time I tried to use them. So we're going to try it out, see why it's wrong. Okay, so to use the new SIMD intrinsics, you need to import these namespaces: system runtime intrinsics x86 and system runtime intrinsics. Now what we're going to do here is we've set up kind of a pretend scenario that could be like a game or a physics simulation. We have these entities, and entities have various properties on them. We've got name, mass, elasticity, strength. And then most importantly, we have these two vector threes. These are three-dimensional vectors representing the current position of the entity and the current velocity of the entity. And then our vector 3 struct is just 3 floating point values. We've got a constructor and we've got some methods on here. So we've got add and normalize. So add just adds 2 vectors together. And this is in the physics sense, where if you have a vector going this way and a vector going this way, you add them and you get a new vector pointing in the direction of the sum of those vectors. And then normalize, what normalize does is it takes a vector and gets a new vector that points in the same direction but is of unit length, right? So if you have a vector pointing north 2 units, normalizing it would make it point north 1 unit. And it does that by getting the length of the vector and then dividing each component by the length. All right, these are very common things you do in vector libraries and stuff. All right, then we're going to go to this benchmarks project. And this is going to do, it's going to set up a 100,000 entities. It's going to give them some random positions and some random velocities. And then our benchmarks are going to go through each entity and just add the position, right? So imagine you had a bunch of things like flying around in space, and they're moving along their velocities each turn of the game or the physics simulation. And we want to see how long it takes, how long each tick of the simulation takes to add these positions to 100,000, add these velocities to 100,000 positions. All right, so we've got our regular add already set up, right? We just do 3 adds. So if you want to use SIMD intrinsics to speed this up, one thing that immediately jumps out is you can do with SSE, which is 128 bits wide, you can do 4 additions of floating point values at a time, right? And we've got 3 additions in a row right here. So that seems pretty good. Why don't we do all 3 of those additions with one SSE instruction instead, right? So that would be as simple as sse.add, right, our 2 things. But we need to take our 3 values and put them into a SIMD type that we can add, right? So what's SSE expecting? It's expecting a vector 128 of floats. Okay, so we need to get a vector 128 of floats somehow from our x, y, and z values. So how can we do that? So there is a vector128.create, and it's got lots of overloads, but one thing we can do is just give it 4 values, right? So we can give it x, y, and z, and we're not going to need the 4th value, so we'll just give that a 0. I'll call that a. Let's see, why is this unhappy? Oh, just because I don't have to say v. Float to int. There we go. Okay, so now we have vector 128 floats a and b. So now we can call sse.add a and b. And we get our result. But now we have to put this result, store it back into our x, y, and z. So how can we do that? So there is a way to get individual elements from our SIMD value. So what result looks like right now is it looks like an array. with 4 values in it, right? So it's going to be like, let's say the answer is 2, 4, 3, 0. It's going to look like an array with 4 values in it. It's just contiguous memory with 4 different floats in a row. And they're actually in reverse order. So it would actually look in memory like this. Right, the 0 is at the end, but in memory it's going to be backwards. But C# doesn't really give us a way to work with that memory directly unless we do a bunch of crazy casts and stuff, which we're not going to do here. But it does give us a way to get individual values out of it. So we can take our result and say get element 0. And that gets us what we think of as the first element. It's actually dealing with that backwardsness for us, which is good and bad. It's bad because it's not the way SIMD programmers are used to thinking. 1, 2. All right, so that'll do the same thing as this add. Now we only have to do 1 plus operation. So let's see how that works. So we're going to use our benchmark. And for the benchmarks, I'm using a library called benchmark.net, which makes it really easy to set up benchmarks that are run properly and run enough times to be sure you're getting a good result. So we're going to compare adding each entity with our regular add, and then adding each entity with our SSE add. And I'm going to run this from the command line because it is better to do so from the command line because then the debugger doesn't attach. So you just need to go to benchmarks, bin, release, netcar app3, and then you can run benchmarks. And what this will do is it'll run each function a few times to warm it up, and then run it a bunch of times to try and get a good sample size to get an accurate result. And since I'm streaming, the values will be a little off, but we're not looking for nanosecond differences here anyway, so it will be fine. Oh, I didn't build. Let's do it again. Any questions so far while this is running? Feel free to bug me in chat, I don't mind. Okay, here we go. So you'll see that benchmark.net tells us a lot of stuff about the environment we're using. So you can like copy and paste these results to someone else and they know details about your hardware and software environment and stuff. But here's the final results we've got. So the regular move entities took 116 microseconds and the SSE move entities took 409 microseconds. So it's actually a lot slower, which is no good. And there's a couple of reasons it's a lot slower. The first reason is doing this create, like loading these values into the SIMD value is taking a lot of time. And then getting them out again is taking a lot of time, right? We're having to get different values out of memory, put them into a new chunk of memory or into a register where they're all contiguous. And it turns out that this is really slow. This is really slow. And it is wasting more time than we save by doing a single add. Now, there are some things we could do if we used unsafe and some nasty trickery. If we specified that this vector 3 had a contiguous alignment in the struct, you can do that with an attribute. And if we put some padding in here so that we had a 4th value, then we could do some casts to like cast our struct into a SIMD value and then do the same thing to cast our SIMD value to an array and get these values out faster. And we might be able to get this performing a little bit faster than our add. But there's still some fundamental problems here. The first of which, of course, is that our SSE add can actually operate on 4 values at once, and we're only using it on 3, right? So we're wasting some performance there. Another problem is if we think about normalize, right? How would we write normalized using this approach? So the problem here is, right, you've got these 3 multiplies you could do at once, right? You could do one SSE multiply X, Y, and Z all in one go, right? And then you would have a SIMD register, right? Which looks something like X squared, Y squared, Z squared, and then, right, our leftover. But the next step in normalize is you need to add those all up, right? You need to add these up horizontally, right? You need to add this X and Y and Z. And SIMD instructions don't give you a super efficient way to do that. You can do it, and when people do SIMD the wrong way, they kind of go through the puzzle and figure out how to do it, but it ends up not so fast. All right, and then you need to do a square root on the result of this, and you only get to do a square root on one value, right? There is a SIMD square root, but there's no way to use it if you're using this approach of trying to implement SIMD this way. So it really ends up no good. You end up like, there's no way to make normalized work faster at all, right? You can vectorize some of these multiplies and these divides, but you're wasting your square root and you're wasting time doing the horizontal add. So this is just a fundamentally wrong approach. And what's wrong is that people tend to think about they've got a function and they look in the function, right? They look like inside this add function for opportunities to use SIMD. Like they look for repeated instructions and think, where can I use SIMD to replace things? In order to use SIMD well, you need to actually think differently about how you lay out your data in memory. And instead of trying to make your add function faster, you want to make your add function happen 4 or 8 times at once, right? So you use your SIMD across multiple calls to your add rather than trying to use SIMD within your add. All right, so let's look at the right way to do this. So this is the right way, going over to the right way file. So now we have a struct called vectors3. It's plural now. And instead of having an X, Y, and Z, vectors3 has an array of X and an array of Y and an array of Z. All right, so that's a totally different way of laying out our vectors in memory than before. And the add function on vector, right, is now iterating through the array of our X, Y, and Z and adding all of them up at once. And then if we go to our entity, we have the same thing here. Instead of just an entity, we have entities plural, and each entity has an array of names, a vectors3, a vectors3 velocity, and then an array of mass, elasticity, strength. So laying things out this way is kind of awkward to people who are used to traditional C# object-oriented programming. And you don't have to totally do things this way. Like I've made everything arrays inside of a struct, but you don't have to do that. Another way to approach this is your entity could remain normal, right? Because maybe most of these things like name, mass, elasticity, maybe you're never doing anything like super high performance with these, so you don't need fast access to these, but you do want fast access to these. So what you can do is have like a singular entity, and instead of having a vectors3, right, your position just becomes an integer that indexes into the vectors3, right? Tells it what index to look at for its X, Y, and Z. So there's various ways to approach this, and you can balance convenience and speed. There are a lot of ways in which this layout is more convenient, which we'll see when we do our new SIMD implementations. But there are also some ways in which it's less convenient, right? Like if you imagine you wanted to delete an entity from your entities, you can't just remove the one entity, right? You have to adjust all of these arrays, right? And your position and velocity arrays to remove that element. So remove becomes difficult, or you have to approach remove differently. But some things become easier. So let's see how we would do our SSE add in this new approach. First thing you'll notice here is I have this crazy fixed syntax. What I'm doing here is I'm getting pointers to these arrays and then using the pointers when doing math. And the reason I'm doing that is to get rid of array bounds checks, because the add operation is so simple. If we have array bounds checks in here, that time spent array bound checking will overwhelm our benchmark results. And what we really want to just compare is, you know, how fast is it to add the regular way versus the SIMD way. So we're going to kind of take array bounds checking out of the equation so it doesn't confound our results. So each of these is just getting a pointer to each array, and then from there using those, because you don't get array bounds checks when you're in an unsafe block using pointers to use your arrays. So that's all that is. Okay, so let's do add the right way now. And I'm absolutely pulling up notes on the other screen to cheat. Okay, so we're going to have the same fixed business going on. And I will explain why in just a moment. Okay. So in order to get data into a SIMD type efficiently, we don't want to call SSE create. We want to call load vector 128. And what load vector 128 wants is a pointer. All right? So in order to get a pointer in C#, you have to have an unsafe block, more or less. And in order to get a pointer to an array, you have to fix it in memory, right? So in a garbage collected language, things can move, right? Something could be at a location in memory and move, and the garbage collector just fixes up all the pointers. But the SIMD load instruction can't deal with that, so we need to fix our arrays in memory in order to get pointers, right? So this syntax says, give me a pointer to a floating point value, and we're getting one from each of these arrays, starting at position 0. But we don't want... Yeah, that's right. All right, so once we have a pointer, what we can do then... Oh, we have to do... X. Oh, we're going to need a loop first. So for int I equals 0, I is less than the length of our array. Okay, we're going to iterate through a whole array, and since we're using SSE on floating point values, we can do 4 at a time. So we're going to increment I by 4 each time. And then we get a reference to our AX pointer at position I. Let's see. We're going to rename these all to pointer. For clarity. Okay, so this now gives us, if you see the type int, a vector 128 of float. And this is actually basically just telling the compiler that we want this data in a SIMD register. So it looks like we're going to have a lot of code here, but it's not actually doing very much. Code, like normal code, that's just saying like A plus B up here, also has to put things in registers. You just aren't explicitly typing that out. So it's not any extra stuff happening here than would happen here. You can't do anything to something without putting it in a register. All right, so we got our AX, YZ, we need our BX, YZ. And then what we're going to do is we're going to store the sums. So again, store needs a pointer. So let's do the same pointer as here, because this add adds v to this, adds v to itself. So the result of our add is going to go there. Let me do this for X, Y, Z. Okay, so that's all of our code. is our add instructions. Right, they're adding 4 of the values from each array at a time. Right, all this code isn't going to take much time because that's just loading things into registers, which has to happen anyway. Right, the compiler would emit the same thing for this. And same thing with storing. That's taking the value in the register and putting it back somewhere in memory, which again would have to happen in this code as well. So really the only code that's happening here are these adds. Right, so the code looks big, but it should be fast. So let's test the theory. Let's go to our benchmark. So now we're going to do benchmarks SOA. It's a separate benchmark class here that does the benchmarks on the right way stuff. So the same thing, we're just setting up 100,000 entities. And we're going to do the regular move where we call add, and the SSE move where we call SSE add. And you'll notice one convenience of laying things out this way is that if you imagine this were a game library or a physics library, you just call entities.position.add and it adds all of them, right? You don't have to do your loop here because your loop is in here. So that can be nice. So let's build this and try it out. Build succeeded. Any questions so far while this runs? Okay, the results are in. So regular move, 101 microseconds. SSE move, 34 microseconds. So now we're seeing almost a 4 times speed up, right, in performing those adds versus the regular way, which is kind of what we expected, right? We expect about a 4x speed up because we're doing 4 at a time, and we get pretty close to that. Now, a more interesting thing here is that you'll notice that our move entities here, 101 microseconds, is a little bit faster than it was before when we had things laid out the other way, right? 116 microseconds. So what's the reason for that? So the reason for that is when we are iterating over our entities in the wrong way code, right, using the normal add, right? The benchmark is, right, iterating over each entity and performing the add. We are having to load in all of this entity, right, all of this data from RAM into the CPU, right? The name, the position, the other position, the mass, elasticity, and strength. And that's a lot of data. And we start to stress the throughput of the RAM, but we also don't leverage the CPU caches very well, right? When you ask for something from memory on a computer, you don't just get the thing you asked for, you get the next few bytes as well. And it does that on purpose because RAM has really bad latency. It takes a long time to get something from RAM. So when you ask for something, it goes ahead and prefetches the stuff after it, expecting that it's likely you'll ask for the things after it. So when we ask for our entities, we're getting all of this stuff when really all we wanted was the data and position and velocity, right? So we're paying a penalty because we're going to more often not have things in our CPU cache that we're trying to access, and we're going to have to go to RAM to get it, which takes longer. And we're also stressing the throughput of our RAM more because we're pulling all this data from RAM that we don't actually need, and we're just adding the X, Y's, and Z's. When we refactor things this way, you'll notice that the adds only iterate over the arrays. No entities are loaded at all, and the data and the arrays are all contiguous in memory. So that prefetching operation is always working perfectly. So, right, as we go through this loop, we're always getting things in the CPU's caches. So everything's very, very fast. So even when you don't actually use SIMD instructions, laying out your data as if you would be using SIMD instructions can make things a lot faster sometimes, right? And I've, of course, contrived this example to make that work out. It doesn't always work out that this is better, but it can be. It often is. It's always good to iterate through memory in order and only iterate through what you actually need. Anytime you add more to your memory throughput, you're going to slow things down. All right, so that's a free bonus you get by organizing things in a SIMD friendly way. This stuff gets faster even in the parts where you aren't using SIMD explicitly. And then, of course, when you can use SIMD, you can get this really big speed up. All right, so that's cool. So what about normalize? Can we make normalize work now using this approach? So let's give that a try. All right, so normalized starts out similar. I'm going to do copy in pasta because time is precious. So we don't need a B this time because we're only working with this. Okay, so we only need pointers to this.x, this.y, and this.z this time because we're only operating on ourselves. And we only need to load AX, AY, and AZ. So that's all set. So then we need to calculate the length. So this is where SSE can be a little painful to work with, or intrinsics can be painful to work with, unless you set up operator overloading. Because we need to do this addition of all these multiplies, so it's going to look a little goofy. So we're going to do SSE add of SSE add of SSE multiply. All right, so AX times AX to get AX squared. Multiply BX, BX, oh, sorry, AY, AY. So that's one of our adds. And then we do SSE multiply again of AZ, AZ. Clear as mud, right? So we're adding the add of multiplies. Let's see, what do we have here? Oh, excess comma. Okay, so that gets us the sum of the squares. And then we want square root. So we can do E dot square root of all of that. And that's our length. So that's wonderful. And then we just need to store the result back into our array. Of the division. So we divide each component by length. Y and Z. And that's it. That's it for normalize. And so we can go unlock our benchmark for that. Did we not do normalize benchmark? So we will. That's why I'm doing the practice. All right, let's build it and benchmark it. Any questions or comments so far? Time is going well. We're not at an hour yet. I also set up benchmark.net to go quickly rather than accurately, so that this wouldn't take forever. But it will be accurate enough for our purposes. All right. So here we have the regular normalize 641 microseconds and SSE norm 95 microseconds. Much, much faster. In fact, more than 4 times faster in this case, which is cool. And it turns out we can make it faster still. So in normal C# code, well, actually maybe you do. Let me see something. System.math. No, we don't. So this divide operation is a little bit slow. It'd be faster if we could do a multiply. So one way we can do a multiply is to calculate the inverse of the square root, right, which would be one divide, and then do multiplies. So that's something you can do here, and it sometimes speeds it up, sometimes doesn't. But the SSE instruction set has a reciprocal square root built in. So you can get 1 over the square root with a single instruction, right, 4 at a time. And so if we get the reciprocal square root, then we can change these to a multiply. So this is an example where sometimes you can get some speed ups from the SIMD instruction sets just because there's some extra instructions lying around that you don't normally have access to with the regular scalar instructions. So let's build that, see how much it speeds it up. Right, so we're doing a possibly slightly more expensive reciprocal square root. I don't actually know if it is more expensive. But we then get the faster multiplies instead of divides. So let's see, this will tell you some performance information sometimes. So 4151 for r square root. This actually looks worse. So reciprocal square root is faster, maybe? That's interesting. Today I learned. Oh wow, norm sped up a bunch that time. Let's run it again just to see. I wonder if the computer like installed an update right when we ran that test. Huh. It's flipping back and forth a bit. That is interesting. But you can see that SSE norm actually got a lot faster, right? We were bouncing around 60 microseconds, and it's been consistently around 30 by using that reciprocal square root. Okay, so next up is how to deal with branches. So this presents a problem because you can't stick an if statement in the middle of some SIMD code, right? Because some of the parts of your SIMD result might go one way through the branch and others might go another way through the branch, right? There's no guarantee you're going to get chunks of 4 that are always going one way through your branch or another. So we have here a clamp function, which is doing something similar to normalize, except that if the length is less than some specified minimum value, then it makes the length equal to that minimum value, right? So it won't let the normalize go less than that minimum value. Otherwise, it leaves it alone, right? So if the vector is already longer than this, it leaves it alone. If it's less than this, it makes it larger to match that minimum value. which gives us this one branch here, right? So how can we use SIMD to handle this? And the answer is, what you do is you compute both the results, and then you select the results you want into each lane. So I'll show you what I mean. All right, so again, we're going to start out similarly to normalize. So we'll borrow all of this. Very good. And then up front, we're going to get our true result. Right, because if length is less than min, then we're going to use this min value to adjust the length of the array. So that's going to be our true result that we're going to select. All right, when this is true, we're going to select this answer. And then if it's false, we're just going to select 1.0, which means we'll do this multiply operation and nothing will change. So those are our two results we're going to use to select. So we're going to calculate length the same way. We're not going to use the reciprocal right now. Just do regular square root. And then we're going to make a mask, which is what we're going to use to see when is length less than min in this chunk of 4 SIMD values. And we can do that with built-in SIMD compares, which might seem like a strange thing to exist, but it does, and it's very useful. So we're going to compare length with the min, right, which you've already put the minimum into a vector. So this is going to be a vector that looks like this. Looks like an array of min 4 times. Right, and we need a vector type to work with the SIMD compare. We can't just put min in here. It doesn't take single values. Right, so these are true results. Right, so that's going to give us a mask that's going to look something like an array of true, false, false, true, something like that. Just, all ones or all zeros. And then we need to select the result we want into result, right? So that means like when we have this mask, which is right, true, false, false, true. When it's true in the mask, then we want the true result. When it's false, then we want the false result. So how do we do that? We can use a series of bitwise operations. So all the bitwise operations like and or and not and so on have SSE or SIMD versions. So we can do this. Okay, so we're saying and mask with true result. So when we do that, anytime mask is true and true result is true, we're going to get it. So basically, anytime mask is true, we're going to get our true result. Anytime mask is false, we're not going to get our true result. It'll just be 0. And then we're going to do SSE and not mask false result. And what this says, anytime mask is false, we're going to get our false result. Anytime mask is true, we're going to get just zeros. And then we OR those two things together. What did I spell wrong here? Double 1.0 f, need to say a floating point. Right, so basically what the OR does, it says, okay, whichever one of these is true, and only one of these can be true at once, right? They're mutually exclusive. Select that one into the result, right? So our final result will end up with true result, false result, false result, true result. Right, so it's just using bitwise operations on a mask. Now there's obviously some overhead here, right? We have to do the compare, which you have to do that anyway in regular code. But then you have to do all these bitwise operations, which fortunately are really fast. CPUs are very good at those. But you also have to like create both the true and false result. Whereas in here, you only have to do this math if length is less than min. If it's not, you don't have to do this math at all. We're gonna have to do all this math every time. That's just the nature of SIMD. So we have to go ahead and store All right, we're going to divide AX by length, multiply times result, just like this. And we do this for Y and Z. Okay, so now we can unlock that benchmark and compare our clamps. And I'm going to comment out these other ones to speed things along. So we're just going to do these clamp and SSE clamp. And I'm going to build. All right, so you can see that we are faster. We're not nearly 4 times faster like we were before, but it is still a significant speed up over the regular clamp. Even though we have to do some extra work, right, dealing with the branch, we still get a net improvement, right? Because you're doing all of this stuff 4 at a time, so it's worth it. Okay, so that's how you deal with branches. So next up is AVX. So we've done all this stuff with SSE instructions. What if we wanted to use AVX2 instructions instead? So AVX2 is twice as wide, so we can operate on 8 floating point values at once. So let's see what it would look like porting SSE instructions to AVX instructions. So let's just like copy and paste this whole thing. And then we will convert it. So we're going to make all of our vector 128s are going to be vector 126s. Our load 128s are going to be load 256s. All of our SSEs are going to become AVXs. So let's highlight. So we're going to take all of our SSE, make it AVX, in selection, go for it. All right. So we can see that we're not quite, it's not quite that easy, right? We can't just turn the 128s to 256s and replace SSE with AVX because there are some differences. For one, we need to go by 8 now instead of 4 in our loop. Otherwise, we'll just be overlapping. And the other is that compares work totally different in AVX than in SSE. And so what's happening here is the AVX class actually is an extension of the SSE class. So this is actually calling the SSE2 compare less than because there is no AVX compare less than. The way AVX works is there is a compare. So it looks like this. And that takes the thing you want to compare, the things you want to compare. So length and true results, just like before. And then you tell it how to compare. So you give it a float comparison mode, which is an enum. And we want ordered less than signaling. So you'll see that there's all these options. So ordered less than makes sense. We're doing less than. But there's signaling, non-signaling. Basically what that says is how to deal with nans. Do you want to throw an exception or just let it work? So there's different ways to deal with nans, and you can pick which way you want the SIMD compare to deal with nans. Nans are not in numbers. We're not going to have any nans, so we're not going to worry about that right now. But that is something to keep in mind. That's what that means. Okay, then I think the rest is good to go. So let's give it a try. So it's all the same logic. Ooh, why are these 9? This should be 0. How long has that been wrong for? Oh, it shouldn't be 0 either. It should be I. It does not change how fast it runs, but it will be very wrong. Okay, so let's see how AVX2 compares to SSE. So we'll leave our SSE clamp in there. And run it up against the AVX clamp with the same 0.5 value. Okay, so this is kind of what you might expect. It's about twice as fast, and it's about twice as wide of an instruction set. So that's about what you expect, right? Almost twice as fast. So that's pretty good, but we can do better because not only does AVX give you twice as much data to work with at a time, but it also gives you some new instructions. Most notably is right here. You don't have to do all this mess with doing bitwise operations. There is something built in called blend variable. And what you can do is give it your true and false results and give it your mask, and it will do the selection for you. So not only is that like a lot simpler to work with, except that false and true are in the opposite order I would have expected, it also performs a little faster. So let's give that a try. And by the way, I'm running all of this on the new AMD Ryzen CPU, and this is the first generation of AMD CPU that supports AVX2 in a way that's actually faster than SSE2. So it's kind of neat to see that happening. Previous AMD chips would run the AVX2 instructions, but at half speed, so it wasn't really any different than before. So did we get any change here? It looks like not, actually. We got 49 this time and 49 before. So this could be a case where on the AMD CPUs, it could be that this doesn't give you any speed up over this way. On Intel CPUs, you usually get quite a big speed up. An interesting question there is, does that mean that this is slow on AMD? Or is this fast on AMD? I don't know. I haven't done that comparison. So that is interesting. I'm going to run it again just to see. I'll probably check that out after the stream. Put benchmark.net back on accurate mode and see if there's any difference. It could be there's a small one. And that is something to keep in mind with SIMD Intrinsics is even if a CPU supports SSE2 or AVX2, the quality of the implementation on a particular piece of hardware can differ. All right, so we're reliably getting 49. So that's pretty interesting. So you should still do it this way when you can. For one, it's just easier to read. And on some CPUs, this will be faster, but not all. At least it's not slower. All right, that is it. So we've covered how to deal with branches, covered some of the basics of SSE and AVX instructions, how to lay out our data, and how to approach SIMD in general, which is the most important part, right? Especially when you start trying to leverage the ability to do computations on 4 values at a time. If you don't iterate through memory efficiently, you will just run into memory throughput and latency limitations, right? Your processor is already very, very fast. So if you want to try and make it 4 or 8 times faster with SIMD, you need to be using memory just right so that you can leverage your CPU caches, or you're not going to get any speed up. That's the most important lesson from this. All right, I'll hang out for a few minutes in case there's any questions. I'm going to grab a drink and then I will come back and check chat. And actually, maybe I'll fire this off. Fire the benchmark off in accurate mode. Need to get rid of that. Just run that and see. I'll be right back. All right, looks like no questions, so I will do this little test and then I will sign up. So 49.6, we're running it more accurately. Oh, did I actually build it though? I don't remember. You can see it's doing a lot more runs. Okay, so 48.14 with the blend. And let's go back to the bitwise operations. Another thing that makes benchmarking interesting is on the Ryzen CPUs, they will speed up and slow down based on how hot they are. So as this benchmark runs longer, the CPU is getting hotter and it slows down. Intel's a little different. As long as it doesn't hit a thermal limit, it just stays at a fixed frequency based on what instructions you're using. Which is good for benchmarking, but bad because it leaves speed on the table. pick your poison. So basically no difference. I mean, it's within the standard deviation supposedly that using blend is a tiny bit faster, but basically no difference. So that's interesting. Today we learned. All right. Good night, everybody. See you later.